This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to the discussion. Today we're diving into the fascinating world of fractals, specifically the Mandelbrot and Julia sets. These intricate mathematical objects are visually stunning and surprisingly accessible.
Indeed. The beauty of these sets lies in their infinite complexity generated from remarkably simple iterative rules.
It's almost magical, isn't it? A simple equation leading to such intricate patterns. What initially draws people to these sets?
The visual appeal is undeniable. The Mandelbrot set's iconic Appleman shape is just the beginning. Zooming in reveals endless detail, a testament to the fractal nature.
And the Julia sets, each unique depending on a single parameter, add another layer of complexity and beauty. Let's start with the Mandelbrot set. Can you define it for our listeners?
The Mandelbrot set is defined by a simple iterative process. We start with a complex number, c, and an initial value, z0, typically set to 0. Then we repeatedly apply the formula zl plus 1 equals zl plus c.
So it's a recursive process.
Exactly. If the magnitude of z remains bounded, meaning it doesn't grow infinitely large, then the complex number c belongs to the Mandelbrot set. If it diverges, it's outside the set.
And this seemingly simple rule creates that incredibly complex shape. The simulation uses a threshold, right? If the magnitude of z exceeds 2 after a certain number of iterations, it's considered to be outside the set.
Precisely. The simulation typically uses 256 iterations as a cutoff. The color of the point then reflects how quickly it diverges, providing a visual representation of the escape velocity, so to speak.
So in the simulation, the points inside the Mandelbrot set are typically colored red, forming that famous Appleman shape.
Yes, and the points outside are colored according to their divergence rate, often using a gradient from green to blue. The faster the divergence, the greener or bluer the point.
And the boundary itself is a fractal, meaning it exhibits self-similarity at different scales. Zooming in reveals smaller versions of the overall structure.
Absolutely. That's the essence of a fractal. The intricate detail continues indefinitely.
The simulation's interactive features are key to understanding this. Users can zoom in on specific areas, increasing the resolution.
Yes, drawing a rectangle allows users to focus on a smaller region, revealing finer details that would otherwise be lost at lower resolutions. The reset function returns to the initial view.
Now let's move on to the Julia sets. How do they differ from the Mandelbrot set?
The Julia sets use the same iterative formula, z plus 1 equals zl plus c. However, instead of varying c and keeping z0 fixed, we fix c and vary z0.
So c becomes a parameter that defines a specific Julia set.
Exactly. Each value of c generates a unique Julia set, leading to an infinite variety of fractal patterns.
The simulation cleverly links the Mandelbrot and Julia sets. The point selected on the Mandelbrot set determines the C value for the corresponding Julia set.
Yes, the white point on the Mandelbrot set visualization acts as a control for the Julia set displayed in the adjacent chart. The color shading in the Julia set visualization also indicates the speed of divergence or convergence to 0.
And again, the interactive features allow for zooming and increased resolution. The reset button on the Julia chart returns to the magnified view corresponding to the Mandelbrot chart,
while a reset on the Mandelbrot chart reverts the Julia set to c equals 0 at the original zoom level.
This simulation is part of a larger project focused on using simulations for teaching mathematics. What makes this approach so effective?
Interactive simulations provide a powerful way to visualize abstract mathematical concepts. Students can actively explore the sets, manipulate parameters, and gain an intuitive understanding of complex numbers, iteration, convergence, and divergence.
The side-by-side display of the Mandelbrot and Julia sets is particularly insightful, showing the relationship between them.
Absolutely. It helps students grasp the connection between the parameter C and the resulting fractal structure. The ability to adjust the color shading also enhances understanding.
The simulation is built using Easy JavaScript Simulations, EJS, a powerful framework for creating interactive educational applets.
Yes, and it's an open educational resource, making it freely available for educational use. The credits highlight the collaborative effort of several individuals.
Let's briefly touch upon the mathematical foundations. The use of complex numbers is crucial here.
Indeed. Complex numbers of the form a plus bi, where I is the imaginary unit, allow for a richer mathematical space than real numbers alone. The iterative process is what generates the fractal patterns.
The distinction between bounded and divergent sequences is key to understanding membership in these sets.
A bounded sequence remains within a finite range, while a divergent sequence grows without bound. This distinction determines whether a point belongs to the Mandelbrot set or not. For Julia sets, we look for convergence to a finite non-zero value or bounded oscillation.
The fractal nature with its self-similarity is a remarkable property.
The self-similarity means that zooming in reveals smaller versions of the overall structure, a pattern that repeats at different scales. This infinite detail is what makes fractals so captivating.
The nonlinearity of the iterative equation is crucial for the emergence of these complex structures.
The quadratic term, z, introduces nonlinearity, leading to the unpredictable and complex behavior that generates the fractal patterns. The parameter c plays a pivotal role, acting as a control parameter in both sets, but with different roles in each. In the Mandelbrot set, C determines membership, while in the Julia set, it defines the specific fractal pattern.
So these simulations offer a powerful tool for learning and teaching complex mathematical concepts in a visually engaging way.
Absolutely. They bridge the gap between abstract theory and concrete visualization, making these fascinating mathematical objects accessible to a wider audience.
That was a great discussion. Thank you for sharing your expertise.